Hello everyone. We are going to learn today about the preparation of potassium dichromate K2Cr2O7, and these are a set of reactions that we need to learn under this category. I would try to make it as simple as possible, but in case you have any queries, you may leave it in the comment box and I'll try to help you with them. Let's start with understanding what is potassium dichromate. Now, potassium dichromate itself is basically given by the formula K2Cr2O7, in which we need to focus on this chromium. Chromium happens to be a D block element, or as we famously know it as, a transition element. Being from a transition family, it has two main things. First of all, availability of D orbitals. And second one is variable oxidation state, both of which are correlated. And because of these two factors, chromium holds a very significant place in compound formation. It is one of these elements which are very much famously known for their different oxidation states in different compounds. Let's take example over here itself. K2Cr2O7, if we want to find the oxidation state, finding the oxidation state of chromium, you simply need to take the compound and bifurcate it. So it is 2 potassium plus 2 chromium plus 7 oxygen, giving you overall charge is 0. There is no sign over here, so 0. We know potassium group 1 element plus 1 charge. Chromium we need to find out. And again, we know oxygen belongs to -2 charge. Solving this further, we have plus 2 chromium minus 14 is equals to 0. Together, we get 2 times chromium minus 12 is equals to 0. Your chromium results into 12 upon 2, that is plus 6. So over here, your chromium is going to show plus 6 oxidation state. Finding oxidation state is relatively simple. Do let me know if you want any help or you want some practice exercises to understand how to find oxidation states of elements present in a compound. Now, this plus 6 is not the only form of chromium available. We have another form of chromium available, famously in the formula K2Cr2O4. K2Cr2O4. This is also one of the way in which your chromium is present. Again, you see over here chromium. If you want to find the oxidation state of chromium in this compound, you will be having 2 potassiums plus 1 chromium plus 4 oxygens, leading up to 0. Chromium, here we need plus 1 and 4 times minus 2. So it's 0 again. Plus 2 plus chromium minus 8 is equals to 0. Chromium minus 6. Here you can see that chromium is again giving me plus 6. So it can be present in different compounds. Over here, you could find that it is present twice in the compound, and yet it is yielding the same oxidation state. So depending on what compound it is in, you can always use this particular manner to find out the oxidation state of chromium. From this, we understand one important thing, that chromium is present in 2 formats or 2 ionic forms from the following compounds that we discussed. One ionic form is CrO4 and the other ionic form is Cr2O7. How do these forms differ? We need to know that both these forms carry -2 charge on the subscript. Okay, meaning what? Both these subcompounds are anionic in nature. Now, why am I saying you these things even before starting with the preparation of potassium dichromate? Because potassium dichromate does not simply yield from its ore. There is a set of reactions that needs to be carried out. And only after those conditions and reactions do we get potassium dichromate from the ore. This particular first compound is also called as chromatine. So if suppose I'm adding sodium, so this becomes sodium chromate. I'm adding potassium, it becomes potassium chromate. Let's see over here, this comes to be called as dichromate ion. So when I'm writing Na2Cr2O7, I'm referring to sodium dichromate. And whenever I write K2Cr2O7, I refer to it as potassium dichromate. One thing that I want to hint over here, students mostly by heart these things as it is without understanding why 2 sodium atoms are required and only one of CrO4 is required. If you want to see, CrO4 actually happens to be one full subunit, so CrO4. So it looks something like this. Students often just by heart this and don't know or even don't are not taught the reason behind this. Let me tell you how to go about this. Sodium has a native charge of 1, which we also call as valency, subcharge, everything. It has a 1 charge. CrO4 has a -2 charge. Over here, when we are forming compounds and denoting how many atoms are required, we do not put plus and minus, we just put the number. We cross multiply this. And that is how you get Na2CrO4 1. In scientific literature, we can overlook this one and hence it becomes 2 sodium ions and 1 chromate ion. Try solving it for potassium dichromate and let's see if you can relate with it. Once we have covered this basic core concept of what type of chromium ions we are using, how these compounds are being formed, and what are their names, let's move or jump directly into the topic, that is preparation of potassium dichromate. Here, I will be helping you with various ways in which you can learn. Issue being that there are a lot of coefficients with every compound in this particular chapter of D block. So memorizing all these coefficients becomes tad bit difficult. If you follow the manner that I am trying to teach in this particular presentation, I hope that you would have some clarity on how to go about the reaction. Okay, so first of all, remembering the core concept that if this is a compound, this compound is obviously not present, floating around in the atmosphere. Neither is it hidden like a gem under the crust. No, we need to remove something called as an ore from the Earth's crust or under the Earth. And this ore is basically iron chromite. Now, one might be confused. We want to find potassium dichromate. We want to create potassium dichromate. But over here, I am writing iron chromite. I am introducing a different metal. So do not worry. Everything would gel in. Just pay attention for a minute. Iron chromite is denoted using the compound formula FeOCr2O3. Pay attention. Chromate, just the slide previous one to this, chromate CrO4, dichromate Cr2O7. But chromite, please pay attention, chromite is Cr2O3. Okay, now many of the students find it easy to remember it this way. But while solving or while deducing the equations, I would like you all to remember it as FeCr2O4. It's the same thing, nothing different. In MCQs, definitely you can vouch for FeO.Cr2O3. So from this iron chromite, we are going to process it a little bit using certain reagents and compounds. And we are going to get our first compound, that's a chromate. That's a chromate. Now let me tell you, we need potassium dichromate. So we won't be first utilizing potassium to get a potassium chromate. Rather, we would be going for or opting for sodium. I'll tell you the reason why. These reactions take place depending on the ions and depending upon the complexity of the ions. Okay, so whenever we are starting with this reaction, there are primary three things that you need to remember. That from ore, first of all, a chromate iron would be generated because it's the simplest one, CrO4. And from this chromate iron, we would be generating dichromate ion or dichromate compound. So from easy to the complex compound. Here, if suppose instead of sodium, we used potassium, that's the common logic that if you want potassium dichromate, you make potassium chromate and then you just, increase the complexity of the ion. But no, that is not how this functions due to one important reason. Potassium happens to be extremely reactive. Sodium is little bit less reactive compared to potassium. So potassium, as soon as it comes in contact with chromate ions, it is going to crystallize out of the solution. Problem being, when potassium chromate crystals separate from the solution, it would become extremely difficult for you to convert it into potassium dichromate. So because of this crystallizing and heavy reactivity problem of potassium, we do not begin this reaction using potassium, but rather a mild compound or mild element compared to potassium, that is sodium. So see how we are going about it. We will take sodium. This sodium chromate then gets converted to sodium dichromate. Okay. And from this sodium dichromate, using a displacement mechanism, we would be getting potassium dichromate. How this functions, what all steps, and how we are going to perform this, each and everything I'll be explaining in detail. But for now, please try to understand that we do not form potassium chromate directly. We are going with sodium chromate. Sodium chromate, as we had discussed earlier, is given by the formula Na2CrO4. Sodium dichromate goes by the formula Na2Cr2O7 dichromate, right? And just replacing it K2Cr2O7. One might think, how would we realize or understand when a particular compound is being formed? So the best part about these preparation reactions, they have some color indicators which help you gauge which compound has been formed. Like as soon as you start this reaction, let's say that you have completed a little bit of the reaction and you're going ahead. As soon as sodium chromate forms, you could find that the solution is turning yellow. Mind you, I am referring it to a solution and not a crystal. As soon as sodium dichromate forms, you get orange solution, not crystals. But potassium dichromate, as I told you already, it is going to crystallize out and you're going to get orange crystals. So as soon as you find orange crystals being generated in your reaction, you are 100% sure that potassium dichromate has been obtained. This is the basic layout of the preparation, and with this you can easily understand how many steps we are going to refer. We would be referring it as step number 1, step number 2, and finally step number 3. I think we can start with step number 1 first. Anywhere you find that things are going a little bit fast, you can definitely pause the video, take some time, relax, and do not forget that, it's okay if this is the first time you're referring to this video or to the concept. You're bound to get some queries. You're bound to have some mixed reactions in your brain itself, as how to remember, as to how to revise this, whether you would be able to justify your answer or not. But I want you to take some time for yourself, okay? Just in case this is something you're referring for revision, please make sure you play this video at 1.5x. That would save your time. First step is iron chromite ore, and we are going to form sodium chromate. In examination, many students write it as sodium chromite itself or iron chromate, vice versa. Confusion, confusion, confusion. Please make sure that the confusion resolves with this video. What are we referring or what are we considering over here? FeOCr2O3. And as I told you, rather use it as FeCr2O4. Okay, this is our iron chromite. And we know what we need from this. We are pretty much sure that we need sodium chromate. So it is what? Na2Cr2. Sorry, my bad. Sodium chromate. No, not dichromate. Cr O4. Okay, we are pretty clear of this. Now, if somebody has this particular doubt in mind, why it is FeCr2O4 or something like that? Okay, it's because the formula itself is FeOCr2O3. We have not changed anything, we have just utilized it. Okay, Cr2O3 again gives you a good reaction. So if you want to continue with this formula itself, go ahead, no problem. Okay, now over here in this condition, one thing that you need to remember is iron is undergoing an oxidation reaction. The ore is undergoing an oxidation reaction. Okay, so iron over here is under its +2 charge. Okay, so let's see over here. Fe is in its 2 charge. Cr2O4 again has a 2 charge. We are just going to cross multiply. We are getting Fe2, Cr2O4 twice. If you have learned chemistry enough, you know that 2 and 2 cancels. That's why FeCr2O4. We are clear with this. What I want you to remember, iron is undergoing an oxidation reaction, meaning initially it was what? It was +2 in the reactant side. Now, in the product side, it is bound to lose an electron and shift its charge to a higher number. So iron becomes 3. Okay, let's move on with what is missing over here. We need sodium, right? There is no sodium over here. We find chromium, we find oxygen, all good, but we are not finding sodium anywhere. For this reason, we are going to add carbonate salt. Very good salt, for also called as washing soda, sodium carbonate. Okay, helps in separation as well of the compounds, and at the same time would be helpful in addition of sodium to the compound. Now, one thing that I always tell my students, remember this is like a golden rule. If you find carbonate in the reactant side, you are bound to get some or the other way carbon dioxide in the product side. 90% of the cases, even carbon dioxide in the reactant side would give you carbonate on the product side. So these are some techniques with which we chemistry people try to analyze the reaction. First of all, let's see, iron, we are going to oxidize it, correct? And to add up sodium to the compound, we added washing soda or your sodium carbonate. With carbonate, we know one thing, that if carbonate is present on the reactant side, it is bound to generate carbon dioxide on the product side. I hope this helps you a little bit. Now let's consider this bichara iron. Okay. Iron has oxidized, but it has no other company except oxygen. Only oxygen is left. And we know oxygen carries a charge of 2. So this becomes a compound Fe2O3. Some people call it rust, but do not worry, there is no rusting in this reaction. We are just considering it as a possible product. Okay, Fe2O3. Once you are clear with the situation, here comes the balancing part. And many students find this difficult. How to start balancing? So let me just erase out the iron explanation, as you can even rewind the video and check this. I have a little bit of a plan for, balancing, for understanding how balancing works. Okay, if you follow that, great, it would be really helpful. So step number 1 over here is, first, you're going to start balancing iron. Now, this is because I have tried out a lot of methods and this is how it fits, First, you balance iron, then you balance chromium, then you balance sodium, then you balance carbon, and finally oxygen. One might ask, why such a procedure? You will understand it in a bit. How many irons do we have over here in the product side? 2, reactant side 1. So we are going to give a coefficient 2 over here. So iron balanced. Let's see chromium. We have how many chromiums? 2, 2s are 4. But we find only 1 over here. So 4 chromiums. Sorted. Let's look at sodium. How many sodiums do we have? 4, 2s are 8 and only 2. Add up 4. Okay, sodium sorted. Let's see carbon. Carbon is 4 over here, only 1 over here. You add up the coefficient 4. Okay. Finally, we are left with oxygen. Okay. One by one, you just need to justify the numbers. You need to compare the, if suppose you're new to balancing, which shouldn't be the case technically, but let's say that you are a bit confused on balancing. Take one element each and start balancing, and let oxygen never be involved in the first cases. Reason being, oxygen is rich in both these compounds. So whenever you find an abundance of oxygen in the compound, I highly recommend to get its balancing to the last step. Start with anything. Here, my preference was iron is first, as you can see in the reactant. Then you can see chromium in the reactant, then sodium, then carbon. So I just took up that way. Okay. And you compare the reactant side with the product side. Do not blindly start putting numbers and then haphazardly get confused. Don't create a mess of yourself. Rather, be calm. Pick one element, compare the reactant number of that element and product, how many atoms of that elements are present. And then try to balance out the reactant and the product. Try it at least a couple of times. Believe it or not, balancing either life or study or chemical reaction takes time and patience. So it's not something that you can mess with by complicating. Rather, sit down with a pen and paper, practice it yourself. Last one is oxygen. Now, if you can see here, how many oxygens do we have? 2 4s are 8. I can see 8 oxygens on this side, plus 4 3s are, I can see 12 oxygens on this side. Here I can see on the product side, 4 4s are 16 oxygens, plus 4 2s are 8 oxygens. OX, okay, it's not cross. And I can see 3 oxygens as well, right? So I can see plus 3 oxygens. Totaling it up on the reactant side, I can see 12 plus 8, that is 20 oxygens. Whereas on the product side, I can find 27 oxygens. You can calculate it yourself. 16 plus 8, 4, 24 plus 3, yes, 27. Okay. Reactant is having 7 oxygens less than product. So what are we going to do? We can't just sit and cry over it. We need to have a solution. Solution is you add oxygen on the reactant side. What are we going to do? We are going to add oxygen on the reactant side. Let me just make this a little more spacious so our oxygen can sit easily. Let's add a sweet little oxygen over here and keep other things proper. Okay. Now, how many oxygens do we need? We need 7 oxygens. And as you can see, 2 is already present. So we need to give it 7 by 2. Many of you might recommend writing it 3.5 because 3.5 into 2 is 7. Alas, we try to avoid decimals. We try to avoid fractions in our reactions. Now, here comes the great deal. We find 2 in the denominator, and just now, I told you one important thing, that we cannot tolerate fraction, at least in maximum of reaction. So what are we going to do? In order to eliminate this 2 of the fraction, we would be multiplying the entire equation, that is the reactant side as well as the product side, with 2. Let's see how this works. And if it works, then it's great. Okay. So over here was 2. We know 2 2s are 4. Correct? Over here, we have 4. We know 4 2s are 8. Here we have 7 by 2 into 7. 2 and 2 cancels. We are happy with our whole number 7. Here you can find 4 2s are 8. Next, for the carbon dioxide, again, we can find it to be 4 2s are 8. Then with iron, I think we don't have any kind of coefficient, meaning it's 1. And we know 1 2s are 2, so we are happy with it. 1 2s are 2. And that results into step number 1. Now, many people might be, it's difficult. Don't worry. Take some time. First, try to understand which all reactants are being utilized and what is the expected product. After that, try to deduce out balancing category. So start with the first element, that is iron. Balance out iron, then balance out chromium, balance out sodium, carbon, and finally balance out oxygen. While balancing oxygen, you will notice that some oxygens on the reactant side are less compared to product side. So you need to add some molecular oxygen into the reaction. And then finally, in order to remove the fraction part of it, you multiply the entire equation by 2. Might take you some practice, at least once or twice. I always recommend the first time you write down, write it looking on the board or, along with me. Second time, just have a look. And if you're getting confused, just refer back to the slide, write it down. And the third time should be closing off any kind of slides you have, taking out a different sheet of paper and trying it by yourself. 3-time practice, believe it or not, reaction becomes simple and you become 1 step smarter. Going to step number 2, now believe it. Step number 2 onwards, things start getting pretty easy. Okay. Step number 2, we have got sodium chromate turning to sodium chromate's higher version, that is dichromate. Let's start with this. Sodium chromate that we have got is basically Na2Cr2O7. O4. What is expected out of it? We are expecting Na2Cr2O7. Here, this reaction requires, please pay attention over here, two chromiums. That means it requires an interlinking. Okay, how is this interlinking done? For this, I always recommend Na2Cr O4. Okay, we need 2 times chromium and again more number of oxygen. What are we going to do? We are going to take this particular compound twice. Let's see now. Do we have that? Yes. We are having now 2 chromiums. Only problem is we have 8 oxygens. So how I help people find this? Whenever you are getting your answer, just mark down whichever is the important point. Okay. So we have got Na2Cr O4 and just consider this chromium alongside Na2Cr O4 and take 3 oxygens from here. You get what? Na2Cr2O7. In the bargain, we are left with something. What are we left with? We are left with 2 sodium atoms and we are left with 1 oxygen atom. Okay, we'll try to help them find their new place. For that, we are going to add an acidic medium over here. Our favorite being H2SO4, sulfuric acid. Now, we know that our major product has been deduced out from the given reactant. We are left with 2 sodiums, right? We are left with 2 sodiums. And we are left with 1 oxygen. And we have H2SO4. H2SO4. Those who know this simple logic might be able to resonate that hydrogen is less reactive than sodium, meaning sodium is placed above hydrogen in metal reactivity series. Under that condition, sodium is able to replace hydrogen from its compound. Okay, so this separates out as 2H plus and SO4. Sulfate always carries a charge of 2 minus. We know one romantic love story that whenever oxygen sees hydrogen, especially 2 hydrogen, both of them unite and you are blessed with water. What are we left with? We are left with sulfate ion, we are left with sodium. Let's try to see. Sodium, charge 1, sulfate, charge 2. What is the product we can get? What is the probable product? Na2SO4. Please tell me if you understand this. Do we have 2 Na? Yes. Do we have 1 SO4? Yes. What are we waiting for? It is Na2SO4. Take a minute to see whether it's balanced or not. Seems balanced? Okay, so that happens to be step number 2. Relatively simpler, and believe it or not, it's also easy to remember. Let's go on to step number 3. That happens to be our final step. Step number 3 is now handing over the dichromate to potassium. So finally, chromate is able to go and attach potassium. We are going to take sodium dichromate, dichromate, and we are going to proceed with our final product, that is potassium dichromate. And it's relatively simple, you know, it's Na2Cr2O7. And what are you expecting out of it? You are expecting potassium dichromate, K2Cr2O7. Simple, right? Now, for this, I want you to remember one clear agenda. Sodium happens to be less reactive compared to potassium. We know according to metal reactivity series, potassium would be able to displace sodium from its compound. And that is what happens over here. So you just need to add any potassium-rich compound. You can add potassium chloride. Okay, since we need two potassiums over here, we need two potassiums here. How does this separate? This separates out as 2K plus, 2Cl minus. This separates out as 2Na plus, and this is going to be Cr2O7 2 minus. We know what combines and what's left behind. We know this combines and we are getting our probable product. The two sodiums left behind do not go to waste. Rather, they combine with two chloride ions. And voila, we get our other byproduct, that is table salt, 2NaCl, sodium chloride. And with this, we end with the preparation of potassium dichromate. Simply said, if you wish to just recollect, we started with the ore FeOCr2O3, iron chromite ores. We treated this with sodium carbonate with some influx of oxygen. Okay, and we got sodium chromate. Please refer back why we are starting with sodium. To this sodium chromate, we add in an acidic condition and another amount of sodium chromate to give sodium dichromate. And finally, we played the displacement step and we got our potassium dichromate. I hope you have understood what we did. Keep referring to the presentation again and again. And if you have any doubts, feel free to leave it in the comment box. Signing off. Bye, everyone.